Hey TechnoStuds! As we've seen in prior videos, OSPF can cause a lot of traffic on our networks. Sometimes that can be problematic. But OSPF has a way to deal with that. On multi-access networks, it has a way to elect what's called a designated router and communicate directly to that designated router. So let's get into what is a designated router and what is a backup designated router and what OSPF does on multi-access networks to limit the amount of traffic on these multi-access networks. We're going to kick this video off by talking about the difference between point-to-point networks and multi-access networks. It's going to just be a brief explanation of that, and then we're going to get into an explanation of the multi-access network and a problem with the multi-access network. Really, a large portion of this video is going to be talking about multi-access networks and how OSPF handles those multi-access networks. Then we're going to get into what is the difference between a DR and a BDR, what do those two roles do. We're going to talk about how it chooses the DR and BDR. We're going to get into DR and BDR recalculation, what happens when it needs to choose a new DR or BDR. We're going to get into what is called priority. We're going to get into the router ID, and then we're going to end things off with just a mention about point-to-point connections. So what is the difference between a point-to-point network and a multi-access network? Well, when we're talking about the difference here, we're really talking about the layer 2 protocol. What is connecting these devices? But just to step back just from a little more simplistic view of this point-to-point protocol are two devices that are talking directly with each other. A multi-access network is going to be a network that has at least the potential of many different devices connecting to the same layer 2 network. So something like Ethernet would be an example of a multi-access network, whereas HDLC and point-to-point protocols are point-to-point type protocols there. So that is the difference between point-to-point and multi-access. Here I have 4 different networks. We're going to say that these are all multi-access networks. Let's say they're all Ethernet. And although this one looks like it's a point-to-point, it is an Ethernet. So this router that's connected to it doesn't know it's connected to 1 device, 2 devices, 4 devices, 8 devices. It's not aware of that. So these are all multi-access networks. So what is the issue here? Well, let's take a look at how many neighborships needs to be created with this. So for this first one right here, there is 1 router connecting to 1 router. That is just 1 relationship that's created there. In this network right here, we have 1, 2, 3. There's 3 connections. So with 3 routers, we have 3 connections. Okay, with this network right here, we have 1, 2, 3, 4, 5, 6. So this network right here has 6 different neighborships that it creates. It's 6 different communications that it needs to establish with it. And then this network right here, we see that there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 different connections. So even though we're only adding 1 router each time, the number of connections multiplies, it's exponential. And there's actually an equation for this. It's n times n minus 1 divided by 2 equals the number of connections we have to have. So in this example right here, we have 2, so there's 2 times 2 minus 1, which then is 1 times 2 is 2 divided by 2 equals 1. Or if we have this 5 right here, it's 5 and 5 minus 1, which is 4. So 5 times 4 is 20 divided by 2 equals 10. So this is the equation right here that we have. Now, let's get to the actual issue then. What it is that for every time we create another relationship, that's another device that we have to communicate out to. And so if we have to communicate for every time there's a change, we have to communicate 10 times, that can be really problematic. So it can really swamp your network. It can really overload your network. A change could happen and it could flood your network with all sorts of communications to combat that change, and no other communication is happening during that time then. And so that is the issue here. So what the solution for this is we can elect a single device that's going to be a designated router. And then all of your devices can talk directly to that designated router. And now the number of connections is going to be just how many devices you have minus 1. So in this example right here, we've got 1, 2, 3, 4. So we've just got 4 connections that need to be maintained. And that makes these bigger networks much more reliable and able to function better. So we have the designated router that allows us to establish these communications. But we actually have also a backup designated router. So let's talk about these different designations. So a designated router, we would just label with a DR here, and this device is the go-to. We also have a backup designated router. So if something were to happen with this designated router, we don't have to really do much. We already know who we're going to start communicating to instead. And so that is the backup designated router. We do have one other designator, and that is this druther. And so the druther is going to be any other device on here, any of the other routers that are going to be communicated on here. So those are the different designators on this network. So let's see how that actually is going to solve our problem. We have a designated router, a backup designated router, and 3 druthers on this network right here. Let's say there's a change to this druther right here. And what it's going to do is it's going to send out a communication to the DR. In fact, actually, it's going to be a multicast address. So it's going to be the multicast address of 224.0.0.6. And so the DR is listening, the designated router is listening to that multicast address and is going to get that update. So this is a link state update that it's getting, and it's sent to this DR. And then it's going to update the database that it has, and then it's going to send out a multicast address to 224.0.0.5. And then all of the devices are listening for this 224.0.0.5. And so then they make the changes to all their databases. So, and this is to be specific, it's the link state database that they're changing. So this is how it eliminates a huge amount of communication. When this change happens on this device right here, it doesn't need to send out a communication to each of the devices. It just sends it to this DR device. It updates its database and then lets everyone else know of the update. The BDR's job is just to stand by and listen and update its database. And if for some reason the DR becomes unresponsive, then this backup designator router will step in and take over for the process. So how does a DR become a DR and a backup DR become a backup DR? What is the election process? Well, it boils down to 3 different things. First of all, it's really who gets there first. Who has OSPF turned on first? Who has the router starts up first? Whatever is communicating on this network first, it may be if it's gone through, let's say this DR, it gets started up and goes through this whole process, then it will, before any of the other devices have OSPF turned on, then it's going to become the designated router for this device. And as soon as these devices turn on and start communicating, they'll recognize that. So that is the first selection process. But let's say, most of your test questions are going to rely around, okay, if all these devices are set up the way they are, how is it going to be select the DR? And the answer to that, it first of all chooses the highest priority interface. We can actually set the priority of each of these interfaces on here to a certain priority. And whoever has the highest priority, that's going to be communicated out with its communication, and whoever has the highest priority interface is going to get designated as the designated router. But let's say we don't set the priority on that. Well, the default priority is 1, and if all of these are set to the default priority of 1, then that's not going to be a good selection process. Then it goes to the highest router ID. And there's quite a bit to the router ID. That's actually can be several different things in there, but just realize that each one of these devices has a router ID, and that router ID actually carries out a few functions. So that is going to be an important part of this whole process, is that router ID. Now, a couple things to realize about this is once this is established, it's not going to actively change. So let's say that this device right here comes online and it has all the rest of these have a highest priority interface, or it has the default priority interface of 1. So all of these have 1. This comes online and it's at 100. And so it gets on there. Well, it should be the designated router, right? Well, no, it's not going to actively change who is the DR and who's the backup designated router, and it's not going to actively change all of that. So when this device comes online, it's going to become a druther and is not going to try to fight for the DR and become the designated router. So when does this become a designated router? If it is set to 100 here, and all of these other interfaces are set to 1 by default. If this is the designated router right here, and this is the backup designated router, let's say that the designated router goes down. And so this designated router goes offline. And it could be the whole hardware gets shut down, or something goes wrong on the interface and the interface shut down, or OSPF just turns off on this device altogether. I mean, it could be an interruption with OSPF, the interface, the router itself. So there could be a few different disruptions here. So in this scenario right here, what's going to happen is this backup designated router will now become the designated router. And so now this one has the master database here that it's keeping track of and is going to do all of the communication. But we do have the role of a backup designated router now is open, and someone needs to take that spot. And so that's where it goes through an election, and then this becomes the backup designated router. So that's where that priority is going to come into play when there is a re-election process that happens with all of this. So let's take a closer look at that priority. We said that we set that priority on the interface. And we've already said the default priority for that is 1. So the default is 1. We can set it to be something different. Like we could set it to be 0. If we set it to be 0, that means that this device will not become the designated router. It doesn't have the opportunity to become the designated router or the backup designated router. The number that we can set is between 0 and 255, and the higher it is, the better chance, the more priority it has over the other devices. If the devices are equal, so let's say we set this to 100 and this to 100, and a new election process takes place, then it goes on to our next selection process of, okay, what is the highest router ID then? Now let's talk about the router ID. The router ID is used for a couple purposes. Well, one we've already talked about. if a DR needs to be selected, it will look at the highest priority interface, who has the highest priority on that interface. And if that's not set, or if they're similar, then it will go to, okay, who has the highest router ID? So a router has to have a router ID. It's not just used for DR election. It's also used to verify who people are as neighbors. And so communication happens back and forth using this router ID. So how does a router ID get set? Well, first of all, we can statically set it on it, and that is go into that OSPF process and define what the router ID is going to be, or it has to create it. And what it would do is it would take a look, first of all, to see if you have any loopback interfaces. If you do, it would choose the lowest numbered interface, loopback interface. So if you have loopback 0, that would be the lowest, or loopback 1 would be lower than loopback 2. So it takes a look at that lowest loopback interface, and then it takes on that IP address, which is interesting. Notice that I say the IP address because the router ID actually looks like an IP address. It's the same format. It's 32 bits long. When we set it statically, we set it as if it looked like an IP address. So it takes the IP address of the lowest numbered loopback interface. If that doesn't exist, if there's no loopback interfaces, then it takes a look at the lowest interface number and takes on that IP address. And so that's how it comes up with this router ID for these devices. So this issue that we're talking about, and which is solved by a designated router and backup designated router, really becomes more prevalent, really becomes more crucial the bigger the network is. That's why your point-to-point networks don't really need to elect a designated router. They don't need to elect a backup designated router. So they don't go through this whole process. So this process is really for the multi-access networks. But there are times when our multi-access networks is just 2 devices, and 2 devices are talking back and forth. So for those, we could actually get onto the interface and we can designate this as being a point-to-point. So even though it's technically not a point-to-point protocol or something that's directly from one router to another, we could go and designate it so it doesn't have to go through all of this electing a designated router and all of this process for OSPF to get up and running. A good example of that is our network has HDLC and point-to-point networks here and here. So this process would not take place there. It does take place, however, between this switch and this router because that is a Ethernet connection. It's a multi-access network right there. And so what we could do is we could get onto this network right here, these interfaces, and change that to a point-to-point network right there, and then we would eliminate that whole process there. So there you have it. That is some of the issues with a multi-access network when it comes to OSPF. As the more connections there are and more neighbors that are established, it can really be, that network can become congested with so much traffic. So to alleviate the traffic, we elect a backup designated router and a designated router and send traffic to that designated router, and then that designated router then disperses the information out. So how does a designated router get elected? Well, it does it, number one, just who is first on the link. But after that, if there's any re-elections that happen, then what it will do is it'll first of all choose one that has the interface with the highest priority level. And then if that doesn't exist, or if it's the same across the board, if they're all set to default or they happen to be the same, then it will look at the router ID. Now the router ID is set based off of a few different things. It's whatever is the highest router ID, and it's based off of, first of all, if you've statically set it, that will be the router ID. If it's not statically set, then it will look at the lowest loopback number, and see the IP address. And then if that's not set, if there is no loopback address, then it'll look at the lowest interface and use the IP address of the lowest interface. So that's how it comes up with the router ID. So, and then we finished this video off talking about the point-to-point connections and how the same issue isn't on those point-to-point connections. So there you have it. That is how it gets Alex a designated router and a backup designated router.